Dienes are compounds with two double bonds, categorized into two types. First, conjugated dienes, our focus, which has more than 3p orbitals side by side, forming a pi sigma bicystine, and second, non-conjugated dienes, where at least one sp3 hybridized atom separates the two double bonds. There are three main characteristics for conjugated diene. First, in the hybridized structure of a diene, all carbons participating in the conjugation system are sp2 hybridized, having a trigonal planar geometry, so they all have an unhybridized p orbital where valence electrons move freely. Thus, electron density is delocalized across the entire structure to maximize stability of the system. Second, conjugated dienes can delocalize to the extent of polarization, or separation of charge. As an example, the simplest conjugated diene, butyl 1,3-diene, has three resonance structures, two of which are polarized, and the overall structure is neutral. The middle one is the major and most stable resonance contributor because it has no formal charges, which leads us to the third characteristic, resonance. Since empty p orbitals can be filled by adjacent p orbital electrons, allelic formal positive and negative charges can resonate into the system to contribute to conjugation stabilization, and electron density can be found anywhere along the p orbital at any time.
Diels-Alder reaction, in which we're going to look at a cyclic 1,3-diene that is going to react with a dienophile and added heat and then make a bridge bicyclic ring system. First, we're just going to start by looking at this simple mechanism and then talk about our actual mechanism. The reason why we're doing this first is just to show you what the difference between a regular fused ring system and a bridge bicyclic ring system would be, as well as show you some of the terminology we're going to be looking at, like endo versus exo. So first we just have a regular cyclic 1,3-diene reacting and showing three curly head arrows with the dienophile. With added heat, we form this bridge bicyclic ring system. These two rings share non-adjacent carbons. That one carbon labeled with green on top is the sp3 carbon that is going to be the one atom bridge. And this is what differentiates it from the fused ring system we've seen before. Now moving on to the actual reaction part where we're going to mention the endo and exo attacks. The endo attack is going to be when any substituent, for example C, is closer to the 2-carbon bridge that we've labeled. Exo is going to be where the any substituent Z is closer to the 1-carbon bridge that we have labeled in blue. Now, speaking from this, we can move on to our actual reaction mechanism in which we react pentacyclodiene with the dienophile. The oxygen is going to be Z substituent in this case.
Much like an electrophile, a dienophile is a species that seeks out diene. Since our dienophile has an electron withdrawing group attached, it's more electron deficient and reactive with the electron-rich double bond region of the diene.
We add heat and we can do this in two pathways. One pathway is going to produce the endo product, in which our oxygen is going to be directly under the diene, as shown here. Here we first form the intermediate, and then we can show you the curly head arrows that made this exchange possible. After this, we've formed our product, but this doesn't quite look like the bicyclic ring system we mentioned above. All we have to do is just orientate it in a way. We're going to flip it upwards to show the actual bicyclic ring system that we mentioned above. To form the exo product, we are going to do the exact same mechanism. However, in this case, the oxygen is going to be orientated away from the diene, and the end product is going to have the oxygen away and towards the 1-carbon bridge system, whereas the endo had it towards the 2-carbon bridge system.
This is the correct connection highlighted in the pink bond, forming the 6-membered ring, and the part that was flipped up is in green.
Endo is a major product and exo is the minor product. This is a concerted reaction. And the reason why endo is a major product is because the electron withdrawing group of the oxygen is placed next to the electron-rich diene. And this is an energetically favorable conformation. And the reaction can only occur in this type of orientation, where the diene and the dienophile are directly underneath each other or above. It can't be side by side.